The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are 3 different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I will respond as soon as I can. Alrighty, so today we're going to wrap up the course. Basically, this is the last new material that we'll look at. Monday, we will do a review. Then we'll have a chapter 11 test the day before your Thanksgiving break. That's on Tuesday. And then we'll come back the following Monday, and we've got a whole week that we're going to spend reviewing, and we'll talk more about that later. But before we get on to that, I've got questions to answer from section 11.5, part 2. So here we go. This is 11.5, part 2. We're going to start off with problem number 2, and we'll take a look at that here. So here we go. It says, assume that there are no deposits or withdrawals. So in other words, there's a certain amount of money in the bank, and we're not going to add to that or take away from that during the process. An initial deposit of $9,000 grows at an annual rate of 6.5% for 7 years. Compare the final balances resulting from annual compounding and continuous compounding. All right, so let's take a look at the whiteboard here. We're going to use 2 different formulas. To find the annual compounding, we're going to use A equals P times 1 plus R divided by K to the KT power. And we're told that the initial deposit is $9,000. So P is $9,000. The annual rate is 6.5%. So R is 6.5%, which is 0.065. Be careful when converting the percent into a decimal. That is often where the mistakes are made. And then finally, time is 7 years. Okay, so we're going to use this to calculate the final balance when it compounds. Oh, compounds annually. So that means K is 1 time per year. All right, so A equals $9,000 times the quantity 1 plus 0.065 divided by 1, all raised to the power 1 times 7. Okay, now I've got all those 1s in there, and I could easily simplify this and make it into 9,001 plus 0.065 raised to the 1 times 7, 7th power. And I could further simplify it and inside have 1.065 to the 7th power. Okay, and I could either enter that first one or either the second or third one into the calculator. So let's see what we've got. 9,000 times 1.065 raised to the 7th power. And I get 1, let's see, actually I want to write that down below so I have room for my other calculation. So I'm going to get 13,985.8789. So rounding to the nearest cent, that would be the 7. So the 8 over 1 column would round up. So I'm going to get $13,985.88. Okay. Now, we're going to use the same information, only now we're going to use, instead of annual compounding, continuous compounding. So that means we're going to use this formula. Okay. We've still got the same numbers for P, R, and T. So A is going to equal $9,000 times E raised to the 0.065 times 7 power, which is $9,000 times e to the, let's see if I take 0.065 times 7, I get 0.455. And so now I've got 9,000 second e to the x 0.455, and I get $14,185, and then it's a 560. So rounding off at the 6, the 0 would round down. So $14,185.56. Okay, so with the same amount deposited, the same interest rate, and for the same amount of time, by changing the amount of compoundings, we get what, about $200 more here than we do there. So the number of times that the interest is compounded, the more the better for you if you're the one depositing the money. All right, any questions about that before we go on to the next example? Okay, let's see here. Number 13. So let's take a look here. It says to estimate the number of hours T that a murder victim has been dead, a coroner uses the formula T equals 1 over 0.25 times the natural log of the quantity 98.6 minus T sub s over 82 minus T sub s, where T sub s is the temperature of the surroundings where the body was found. If the crime took place in an apartment where the thermostat was set at 72 degrees Fahrenheit, approximately how long ago did the murder occur? Okay, so we're going to take this formula and we're going to put 72 degrees in for T sub s. Okay. So then our, let's see, T sub s is going to be 72 degrees Fahrenheit. So the time is going to be 1 over 0.25 times the natural log of 98.6 minus 72 over 82 minus 72. Okay. I'm going to do some simplifying of this. For instance, what's 1 divided by 0.25? That's 4. Oops. So then I've got 4 times the natural log of, let's see, in the numerator, 98.6 minus 72 is 26.6, and 82 minus 72 is 10. Okay. We could even go further, I suppose, if we wanted to, and we could say 26.6 divided by 10 would be what, 2.66? Now, understand, we could put all this in the calculator initially without doing any simplification, but it just seemed nice and easy to do. So the natural, 4 times the natural log of 2.66. And let's see here. I keep picking up the wrong pen. This is going to be approximately 3.91 hours. The problem said to round to 1 decimal place, so 3.9 hours. Okay, so the body had been dead, or the victim, whatever, had been dead for almost 4 hours. Of course, I can see a problem with this. Not everybody's normal temperature is 98.6. Some people have a slightly lower or slightly higher temperature, so that could mess things up a little bit. Probably not a huge amount. All right, anyway, we're going to go on to examples. So here, let's see here. Okay, what's up next 4770. Oops. 47. And here, 4.5 part 2, number 5. Okay. So let's take a look at this problem. Number 5, this is again all from 11.5 from part 2. Kuwait, located at the head of the Persian Gulf, has one of the greatest population growth rates in the world. Bulgaria, in southeastern Europe, has one of the smallest. Use an exponential growth decay model to complete the table. Okay, what do we know about the exponential growth decay model? That is that model A, or that formula A equals PE to the RT, okay? Because that's a continuous growth or decay. So let's see, we're supposed to get the estimated population in 2017. So let's talk about Kuwait first. Let's see, Kuwait. We've got the population at the beginning of time, which is 2010, the annual growth rate, and then we want the estimated population in 2017. Okay, so that means our formula is going to be A equals 2,789,132 times E, and then to the RT power, let's see, R would be 0.03501, and time is what, 7 years from 2010 to 2017. So what our formula is going to look like when we put all the numbers in, A equals, we've got the initial population, we've got the growth rate converted to a regular number, and the time 7 years. Okay, and again, I could pre-multiply the 0.03501 times 7, or I can just make sure I put parentheses around the whole thing. Put parentheses around the whole thing, the whole exponent. So 2,789,132 second e to the 0.03501 times 7, close it up. And I'm coming up with, oops, again, I don't want to write there because I want to save that space for the other calculation. Sorry about that. I'm going to come up with 3,563,703.93. And here we would round to the nearest whole person. So that's going to be 3,563,704. So 3,563,704. So the population would go up from roughly 2,800,000 to 3,600,000 approximately. All right. Now, let's take a look at Bulgaria. For Bulgaria, the initial population is 7,148,785. The annual growth rate is negative because the population is actually decreasing. So we're going to take negative 0.768% and convert it into negative 0.00768, and all of that times 7 again. Okay. And let's see what we get here. 7,148,785 times e to the negative 0.00768 times 7, close it up, and I'm getting 6774614.144. So rounding to the nearest whole person, 677,461,4, 6,774,614 people. All righty. And let's see here. Next person. Okay. Just want to make sure I've got the right screen showing before I move things around. And okay, 4770. Here. Yeah, 2.5. Okay, number 10. All righty. Let's take a look. In case you're wondering why I always switch back and forth, it's so you can't see whose questions I'm answering. Discreteness is a must, or something like that. Okay. So now we're going to look at number 10. It says, before the parachute opens, a skydiver's velocity in meters per second is modeled by the function f of t equals 50 times the quantity 1 minus e to the negative 0.2 t power, where f of t is the velocity at time t. Find the velocity after 20 seconds of free fall. All right. So let's see here. We need to find f of 20, basically. So f of 20 would be 50 times the quantity 1 minus e raised to the power negative 0.2 times 20. Okay. And let's see here. Got lots of grouping symbols there. I'm going to simplify that a little bit. 50 times 1 minus e to the, if I take negative 0.2 times 20, I get negative 4. Okay. So 50 second e to the x. Oh, nope, wrong. 50 parentheses 1 minus, and then e to the x, and my exponent is a negative 4. I need to close up my exponent, but then I also need to close up the entire quantity, okay? And when I do that, I get 49.084, et cetera, round to the nearest whole number, so 49 meters per second. Okay. Now we're going to take a look at problem number 12. We good to go on? I'll take that as a yes. Number 12 says a population growing continuously at an annual rate will triple in the time given by the formula t equals the natural log of 3 over r. Okay, so again, let's take a look at that. Population growing continuously at an annual rate r will triple in a time t given by the formula. And we talked about this yesterday, how if it was the natural log of 2, it would double, the natural log of 3, it would triple. How long will it take the population of a town to triple if it is growing at a rate of 13% per year? Round your answer to 1 decimal place. So basically r is going to be 13% or 0.13. So I'm going to find time, which is the natural log of 3 divided by 0.13. And so going to the calculator, we get the natural log of 3, close it up, divided by 0.13, and I'm coming up with 8.450, et cetera, years. Round to 1 decimal place, the 4. Going to the right 1 place, the 5 would round up, so 8.5 years. Okay. And finally, number 13, which is just like one we did earlier. I'll take a look at that and just talk you through it here, and then we're going to go on. So the problem we did earlier, I believe the temperature was like 72 degrees. So this problem, same thing, only instead of putting 72 in for T sub s, you're going to put 70 in for T sub s. Simplify the numerator, simplify the denominator, punch it in, good to go. Okay. If whoever requested that still needs it, get in touch with me later and I'll be happy to go through it with you, but it was just like the one we did. Okay, so with that, we're going to move on. And so let's see here. I want to go back to a problem that I introduced early on in this chapter. And I said something like this: 2 cubed is 8, 2 to the 4th power is 16, 2 to the x, and I said pick some number between 8 and 16. And I don't remember what number was chosen, but you know what? We can just pick one. So give me a whole number between 8 and 16. Just anybody there? Somebody, please? Somebody?
11.
11, thank you. 11 it is. All right. So we need to find out 2 raised to what power is 11? Well, we know that x is greater than 3 and less than 4, so it's got to be 3 point something. But we could spend a lot of time trying to get an accurate answer. So instead, what we're going to do is we're going to take this exponential equation and we're going to write it as a logarithmic equation. Log base 2 of 11 equals x. I'm going to actually turn that around and write it as x equals log base 2 of 11. Well, that's fine and dandy, except that on most of our calculators, all we have is log base 10, that's log, and log base e, which is ln, okay? Some of the scientific calculators actually have a button that has this. You can put in any log you want, but not everybody has it, so we're going to assume that nobody has it. What we need to do now is we need to take this and use what is called the change of base formula, which will allow us to convert that information into something using either just log base 10 or just log base e. Now, the formula, which for those of you that have the textbook, it's on page 969, but the formula says this. It says log base b of x equals log base a of x divided by log base a of b. Now, base a, we want to use either base 10 or base e, because if we use base something else, it's kind of pointless. The whole point here is to switch it into something we can punch into our calculator. So notice that this is up here and this is down there. So this would become the log base 10 of 11 over the log base 10 of 2. Now, technically, I don't need to write the 10, but I'm just reminding you. So we could write it like this, and that would get our answer, which we'll go back and get in a minute. Or we could write it as the natural log of 11 over the natural log of 2, which would give us the same answer. Now, understand this. Log base 10 of 11 does not equal the natural log of 11. Log base 10 of 2 does not equal the natural log of 2. But the ratio of this fraction is equal to the ratio of that fraction. They've got to both be log base 10 or both be log base e. You can't have one of them 10 and one of them e. Okay, they got to be the same. All right, so log of 11 divided by the log of 2, and it comes out to 3.4594. And let's see, I'm going to take it out to 4 decimal places. There's a 3 there, so the 4 would round down, so I'd get 3.4594. Now I'm going to go back and do the same problem with the natural log of 11 divided by the natural log of 2, and I get the same answer as I should. So basically what this means is this number, which again has been approximated, would go right there. So 2 raised to this power would be 11. Now I said approximately. Since we rounded this off, it's not going to come out exactly. It's going to be like 10.9999 or something like that. But to 4 decimal places, that's what it would be. Any question before we look at some more examples using this change of base formula? All
Are
right.
we done going 11 or are we done going over 11.5 part 2?
Yes, I'm sorry. I didn't ask if there were any other questions. I should have. Did you have some other questions?
Yeah, I asked you if we could go over number 4 yesterday and we said we could today.
Number 4. Okay, sorry, I somehow forgot that or overlooked it. Okay. Is it complicated? Can you just tell me, or do I need to look it up?
I can read it to you real quick.
Okay.
It
Sorry
says
about that.
the population of Earth is approximately 6.8 billion people and is growing at an annual rate of 1.133%. Use the exponential growth model to predict the population in 45 years.
Okay. Now,
It says round your answer to 1 decimal place.
the 6.8 billion, is it 6,800,000, or is it 6.8 and then the word billion?
It's 6.8 billion, like the words.
Okay. So what that means is in our answer, we're going to write it so much billions with the word billions. Okay. So we've got this. So A equals 6.8 e to the 0.01133 times 45, and this is in billions. Okay. You all right with that?
Yes.
Okay, so now 6.8 e to the 0.01133 times 45, close it up, and I'm getting 11.32. And you said to 1 decimal place?
Yes.
So 11.3 billion is what the answer should be.
Okay, thank you.
You're welcome. Was that all?
Yeah, that's the only question I had.
Okay, thanks. All right, so now we're going to go back to looking at some examples. What? Somebody else have something? No? Okay, sorry. Using the change of base formula. For instance, log base 3 of 7. Okay, so that would be, I can use log base 10, or I can use natural log. Either way. Okay, so let's see here. Log of 7, close it up, divided by log of 3, close it up, 1.77124. So the 4 would round down. Same thing here, 1.7712. How about log base 1/2 of 6? That would be, I'll go natural log of 6 over natural log of 1/2. And so natural log of 6, close it up, divided by natural log of 1/2. And I'm getting negative 2.58496. So the 6 is going to round up. And again, I could have also done it using log base 10. We okay with that? Do you need any more examples of that? All right, that's all we're going to do in 11.6, and you'll see in the homework tonight, you've got section 11.6 and 11.7, but there's just a few questions from 11.6, basically just dealing with that change of base formula. Okay, so now we're going to go on to section 11.7. And so far, we've got, let's see, we've got this formula, which is for compound interest that is not compounded continuously. We've got this formula that is for continuous compounding or continuous growth or continuous decay. So if it's continuous, we use the formula with the E in it. If it's not, we use the first formula I gave. There's another formula I want to look at, but before I do, I want to just kind of go through something to make sure you get what's going on here. Let's say I had y equals 2 to the negative 3 power. Is that the same as y equals 1/2 to the positive 3 power? No one
Yes.
knows. Yes, it is, right? Or if I had y equals 4 to the negative 7 power, that would be the same thing as y equals 1/4 to the 7th power.
Yes, because don't you have to get the
Reciprocal.
power to be positive?
So you take the reciprocal of the base and then change the sign of the exponent. Okay, so if I had y equals 2 to the x, rather, wait a minute, that's not what I wanted to say. Let me erase that. If I had y equals 2 to the negative x, is that equal to y equals 1/2 to the positive x? Are those the same?
Yes.
Okay, now, we talked about how if you've got a problem in this form, if b is greater than 1, this thing's going to be increasing. If b is less than 1 but greater than 0, it's going to be decreasing, right? But that was all when this is a positive x or positive exponent. If we had this, that's the same thing as that. So now we end up with a decreasing function. So what I'm trying to get at is this, okay? Even though this base is larger than 1, because of the negative exponent, it's going to be a decreasing function. Now, I said all of that to say this. Here's the new formula we're going to look at. It says a equals a sub 0 times 2 raised to the negative t over h power. Okay, now the base is a 2, but because the exponent is negative, this is actually a function where it's going to be decreasing, because they could have written it 1/2 to the t over h power. For whatever reason, they didn't do that. If it was me, I would have done it that way, but that's not how they did it, okay? So this formula has to do with radioactive decay, or what is called half-life, all right? Now, how does half-life work? Let's say that I put 32 Snickers bars in a refrigerator, and I came back 1 week later, and there were 16 Snickers bars. So half of them were left. And then I came back 1 week later, and there were 8 Snickers bars. And I came back 1 week later, and there were 4, and then there were 2, and then there were 1, and then there was a half, and then there was a fourth, et cetera, et cetera. So every time 1 week goes by, half of what the population was at the beginning of that week goes away. So it's not like you lose 16 the first week and the other 16 the second week, and so after 2 weeks it's gone. No, each week, whatever's there at the beginning, you lose half of it. So for this particular problem, we would say the half-life of a Snickers bar is 1 week. Okay. Now, okay. We're going to come back to that idea in just a bit here. First, I want to look at something very similar to what we've done before. Let's say we had 3 to the x plus 1 power equals 27. And it says solve each equation, all right? If we could take this equation and write it so that it had the same base, for instance, 27 is 3 cubed, now that the bases are the same, the exponents are also the same. So that means x plus 1 equals 3, so x equals 2. Let's check our work. If x is 2 and we put it right up there, 3 to the 2 plus 1 power equals 27. 3 to the 3 power equals 27. 27 equals 27. It checks. Any questions on this example? All right. Let's take a look at another example. 8 to the negative 2x plus 1 equals 1 over 64. Well, I could take 64 and write it as a power of 8. That would be 1 over 8 squared, or 8 to the negative 2 power. So leaving the left side as it is, taking the right side and writing it as 8 to some power. Now, because the powers are because the bases are the same, so are the exponents. So our equation becomes negative 2x plus 1 equals negative 2. Solving for x, subtract 1 from both sides, divide by negative 2, x is 3/2. Any questions on that problem? Okay. Let's say we've got 7 to the x power equals 12. Well, following the examples before, I need to take 12 and write it as 7 to some power. I have no idea how to do that, okay? So I'm going to have to use a different method. Well, this is an exponential equation. The variable is in the exponent. If I rewrote this as a logarithmic equation, I would have log base 7 of 12 equals x, right? That goes back a couple sections. I'm going to just turn that around and write it as x equals log base 7 of 12, because now I'm going to use this change of base formula that we looked at a little bit ago, and I'll write this as log base 10 of 12 over log base 10 of 7, and go to the calculator. Log of 12 divided by log of 7. And I'm going to write my answer approximating to 4 decimal places. Let's see, I get 1.27698. So the 8 would round up. So I'm going to get 1.2770. Okay, so 7 raised to approximately that power would give you 12. Any questions? Okay, let's take a look at another example. E to the 3.3 t power equals 9.1. Here again, I have no way of knowing how to take 9.1 and write it as e to some power. So those first 2 problems I showed you work if you can get the bases the same easily. But if you can't, then you basically have to take this and change it to a logarithmic equation. Log base e of 9.1 is 3.3t. Now, log base e, isn't that natural log? So I could write natural log of 9.1 equals 3.3t. But I'm trying to solve for t. So what would I do next? Divide both sides by 3.3. So t equals the natural log of 9.1 over 3.3. Now in this case, I don't need to use the change of base formula, but keep in mind, you're just taking the natural log of 9.1, close it up, divided by 3.3. So natural log of 9.1, close it up, divided by 3.3, and I get approximately 0.66917. going out 4 places. The 7 rounds up, 6, 6, 9, 2. Okay with that? All righty. I introduced that whole idea of half-life, and then I didn't do anything with it. I just wanted to get the new material out there. Now we're going to go back and we're going to do some problems involving that half-life formula. Okay. Here's a problem. It says radioactive decay. All right. So radioactive, we're talking about a radioactive substance. So half-life pertains to that. And we're talking about decay. So it's going to get smaller, half-life kind of thing. It says in 2 years, 20% of a radioactive element decays. Find its half-life. All right, so first of all, the half-life formula was A equals A sub 0 times 2 to the negative T over H power. Okay. In this formula, T stands for time. H stands for the half-life of the substance. A sub 0, think of it as A with a little O as in original. So AO would be the original amount, and then A on the other side of the equal sign is the final amount. Okay? They tell us that the half-life of this of tritium is 12.4 years. How long will it take for 25% of a sample to decompose? So 25% decomposes. All right. Now, I'm trying to find how long it takes. No. Yes, how long it takes. Sorry, my bad. I don't know the beginning amount, and I don't know the ending amount. Okay, I do know that the half-life is 12.4 years. I know that time is what I'm trying to find. I don't know the beginning amount, and I don't know the ending amount. But here's what I do know. I know that during this time that we're going to find, 25% of the original amount decomposes. If 25% decomposes, what percent is left at the end?
75%.
Right. So the beginning amount is A. The ending amount is 75% of A. You see how I got that 0.75? 25% decomposes, 75% is left, converting that into a decimal, 0.75. All right. So now we're ready to put this into the formula. So, oh, you know what? My bad. I did this backwards. I am so sorry. I did this backwards. So if you were confused, I'm feeling like I've got to hurry, and that's not a good thing. So the starting amount was A sub 0. The ending amount was 75% of the starting amount. Okay? Sorry about that. So my equation is going to look like this. 0.75 A sub 0 equals A sub 0 times 2 to the negative T over 12.4 years. We okay? Now I'm going to divide both sides by the starting amount. So 0.75 equals 2 to the negative T over 12.4 power. So just like a problem I did yesterday, where we weren't, well, we're talking about doubling the amount. Okay, we don't need to know what the amount is because it gets divided out before we get to the final answer. So now I've got 0.75 equals 2 to the negative T over 12.4 power. This is an exponential equation. I'm going to rewrite it as a logarithmic equation. Okay, so log base 2 of 0.75 equals negative t over 12.4. We okay with how I got there? All right. I am going to go up here and erase this so that I have a place to write without having to go to the next page. Okay, so I'm going to go back up here. I'm going to multiply both sides by negative 12.4. Because on the right side, the 12.4s will reduce out, the negative times the negative will be positive, and I now have t equals negative 12.4 log base 2 of 0.75. Do you see how I got rid of the negative sign in front of the t and the 12.4 in the denominator? One more step, I'm going to use the change of base formula, which is going to be log of 0.75 divided by the log of 2. And that I'm going to punch into my calculator. So negative 12.4 log of 0.75 divided by log of 2. And when I do that, I get 5.146. If we rounded to the nearest tenth, we would get approximately 5.1 years. So for 25% of it to decay took 5.1 years. Okay. Any questions about that example? Okay. Let's see here. Let's take a look at another problem. This says carbon-14 dating. A bone fragment analyzed by archaeologists contains 60% of the carbon-14 that is assumed to have been initially. How old is it? Okay, so again, A equals A sub 0, 2 to the negative t over h power. A bone fragment analyzed by archaeologists contains 60%. Now, I want to make a big deal out of this next thing because this is where people tend to mess up if they don't read too carefully. In the previous problem, it said 25% decomposed, which meant we were left with 75%. This one says it now contains 60%. Okay, so it's not that 60% is going away. Actually, what, 40% went away, 60% is still there. All right, now, so we've got A sub 0, A, T, and H. We don't know the starting amount, but the ending amount would be 0.6 or 60% of the starting amount. The time is the unknown, and the half-life is given as 5,700 years. Okay, so 0.6 A sub 0 equals A sub 0 times 2 to the negative t over 5,700 years. From here, it's going to look just like the last problem. I'm going to divide both sides by A sub 0. So 0.6 equals 2 to the negative t over 5,700 years. I'm going to change that to a logarithmic equation. Log base 2 of 0.6 equals negative t over 5,700. I'm going to multiply both sides by negative 5,700. So that's going to give me t equals negative 5,700 log base 2 of 0.6. Using the change of base formula, negative 5,700 log of 0.6 divided by log of 2, and then going to the calculator. And we get negative 5,700 log of 0.6 divided by log of 2. And let's see here. I pushed a decimal point instead of a negative sign. Let's try that again. Negative 5,700 and then log of 0.6 divided by log of 2. And it comes out to be 4,200.703. And so approximately, so we'll say about 4,200 years. All righty, well, our time is up. So we've got 2 new formulas to look at, the change of base formula and the radioactive decay formula. I'll be back at 1:15. And then if not, then I'll see you on Monday, where we'll be reviewing for a Chapter 11 test on Tuesday. Have a good weekend, and we'll see you later.
Thank you, Mr. Mayo.
You're welcome.